So we are into our first week and the second lecture, and here we are introducing and providing the background aspects of prognostics and health management systems approach. Okay, and we have emphasized that this approach is AI/ML enabled or centered. Without AI/ML, remaining life is full, because no mathematical formula can provide you this answer, because a lot of uncertainties, non-linearities are built into the prediction. So as the data, online data, they are provided to the system, it provides an estimate by reading the previous data and previous vectors. Okay. So in this lecture, we'll see reliability and PHM. In fact, if in one word I have to answer this, it will be PHM is an advanced version of reliability. Why? Because reliability provides us, reliability is a probabilistic entity. So reliability provides us with an estimate of probability of failure. Probability of failure. In terms of, like, typically it will be 10 to the minus 3, probability will be 10 to the minus 3, 10 to the power 4, 10 to the minus 5, 10 to the minus 2. So 10 to the minus 2 says 1 in 100 chances are failure. Okay. 10 to the power 3, 1 in 100,000 chances are failure, and that gives you confidence how reliable this product is. But again, you see, it is not giving us the instant of failure, it is giving the probability of failure. That means the failure might occur within next 3 days after putting the component into service, or it may go into 3 months, 4 months, 5 months, like that, if you try to estimate. That means the instant of failure is not given. So that job is done by PHM. So you can say PHM is an advanced version of reliability matrix. That means it gives us, or it attempt to give us the instant of failure along with uncertainty. So that means it gives a complete estimate. First, it provides a reliability estimate like mean or median uncertainty bound, upper and lower bound, mean value, and then it says what is the spread of this bound. It is well understood, and we get more confidence that this component will fail if I take the upper bound. That means it will definitely fail before failure. I'll show you on the slide when it comes to in the presentation. But PHM is a advanced version of reliability, because it provides a instant of failure information. Okay, and then we know that this PHM is a predictive methodology. Okay, and reliability fundamentals do form part of it. It is not totally done away, because if I have to estimate the uncertainty, I need distribution. Distribution is an inherent component of reliability engineering. So, but then the main driver is degradation, and based on the degradation, evaluation of remaining useful life. And before we go to the models, methods and all, we'll see life cycle curve. How in a complex, because our subject is a complex engineering system, we are trying to see implementation of PHM in a complex engineering system. So we'll see system specific slides also, we'll see component specific slides also. And now next is data. How the data are received, what sensor does, and how the probabilities are built for uncertainty, and how trends are worked out, and the outcome, and what is the limitation. Probably limitation we have talked about it, but then we have to as the presentation proceeds, as the lectures proceed, we will come to more limitation, more advantages both. And then there is one or two slides on risk characterization, because this particular approach, systems approach, is enabled like AI/ML is used for prediction, this probabilistic risk assessment, and thereafter the risk-based engineering. And when we talk about the operation environment context, then it is a risk-conscious operation management. These things they become part of it, and that's how it becomes a systems approach. And then PHM and reliability, probably I give sufficient sufficient input on this, and then risk characterization, and finally PHM, a predictive maintenance approach. Time based maintenance, breakdown approach we have seen earlier, condition based maintenance, then risk informed, risk based. It is a predictive approach. It is supposed to predict before the incipient failure becomes the reality. Okay, has shown potential for real time applications. Okay, there are some PHM examples. If I go through the literature, these applications, even though in the system they have given results, but the publication is referring to this particular achievements indirectly in terms of models and methods and all that. And that's how complement supplement traditional reliability approach. So here we are not saying that reliability based approaches are not useful. They are very useful. Like here itself in PHM, it provides uncertainty estimate. Then when we call systems approach, the probabilistic risk assessment model, it provides us the way for quantitative approach for identification and prioritization, because PHM cannot be implemented on the complete plant because it is a resource consuming activity, and at the same time it resource also includes financial component, then human components tends to reduce because of this, but then expensive parts and all, and then maintaining those parts also is a we have Internet of Things there, you have to have smart sensors. So it's a very resource consuming exercise. So it should be implemented where 80% problem is solved and 20% where the consequences are not severe, like process systems do not result on their own, do not result into the risk because there are safety system working and guarding them actually. So this is how it is. Now let us spend some time on reliability, because it is just for the sake of continuity that what reliability means and how PHM becomes a extended version or advanced version of reliability engineering. So reliability means failure free operation of a component in simple words. Suppose if the component was a nuclear plant was supposed to operate for 1 year or 2 years, then it should not bring in any interruption. There should not be any interruption. It should operate continuously for 2 years. Even if there is one failure, the reliability is compromised. If there are 2 shutdowns or failures, there is a reliability further compromised. So reliability means failure free operation. And how it is quantified? 1. Reliability is 1 if the mission is achieved successfully, and then based on the failure data, the lower figures are there, but maximum reliability possible from any system is 1. Okay, and if I talk about the reliability definition, probability that the system, structure or component, this 3 phrases, system, structures or component, we will have acronym SSC, system, structures, component, in future slides. So please, you have to get lot of acronyms. You see them, mark them on your slides for effectively studying this subject. So what we say is probability that the system, structure, component or entity, it could be entity, service, okay, will successfully and satisfactorily work without interruption for a given mission T under stated conditions. And now we have this mathematical expression for reliability. Okay, so reliability as a function of time is nothing but probability that capital T is more than small t. That means failure free operation. And like any other attributes, here it has got given that C1, C2, C3, C4 under a given or stated conditions. Let us say if a component was to operate at normal plus 20, minus 20. So that condition, the testing also should be done in that condition, so that this reliability is applicable for component. Like suppose if a company is designing a component for India, and if it is designing a component for a country where the temperatures itself are minus 20, minus 30. So the testing should be done under those conditions, so that it is demonstrated that it is working under those lower conditions, minus 20, minus 30 and all that. Okay, and then these are C1, C2, C3. So the expression can be read as reliability as a function of time is equal to probability that the random variable T will be more than the mission time T given condition 1, condition 2, condition 3, temperature, humidity, dust free environment, whatever condition we want to apply. Okay. So we have this expression, and here I wanted to highlight that reliability is a reducing the moment the component is started. If the component is not started, reliability is 1. The moment component is started functioning, its reliability is continuously comes down because of, you can understand, wear, tear, oil condition, if it is a pump, so many things, So if you maintain it well, then the curve can go like this further. But if you don't maintain it, it will further reduce. So it depends. But one thing can be said: reliability reduces the moment component at time t is equal to 0 comes into the operation. It is activated. So on the x-axis we have t, and reliability is this one function. So third thing is reliability is a function of time. We know that, and t is a number of variables for time t. So it is a random variable, because when you do testing, this t can occupy any value, and those values together they are called random variable. Okay, all the component will not fail at same time. That is the meaning of it. T mission time, that is, if we are designing the component for, let us say, 2 months or 3 months for continuous operation, then T becomes the 1 month or 2 months is the mission time, and C's are conditions here. It is important to know that reliability is now here, as I mentioned, it is reliability has got a probabilistic notion. If the reliability is 10 to the minus 3 or even 10 to the minus 6, it doesn't mean it will not fail within a week. It might fail, but for next 3 years it may not fail. So there is no guarantee on that component will not fail. For that you need to have a PHM. So this is the context. In that term we have noted it. Okay. Now there are many systems in which mission time is not the criteria. It is not a T. Fundamental is not a T. It is cycle, number of cycles. Number of cycles determine the life of like a switch in your house. If how many times you switch on, switch off, switch on, switch off, that many cycle, 1000 cycle, 3000 cycle. Okay, and for particularly for this structural component, So that is another notion of reliability. I said in the previous slide. Okay, so that will be handled, and then factor of safety. Structural reliability normally dealt with in terms of the stress and strength interaction. That means what is the stress level the structure is facing, and what are the strength that is built into the system, and that in the traditionally it used to be called as factor of safety. Factor of safety was basically to account for all the uncertainty that are available when the component is operating or facing the real time condition, and what are the material property, their distribution will be determined here. So mean of strength divided by mean of stress, that will give us factor of safety. And engineering would operate on this particular model, but now more data is available, more computational tools are available, and more insights are available in metallurgy. So now the uncertainty has reduced. So now we can have a better estimate model, that is stress and strength. What are the stresses and what are the strength? And the overlapping area, you can say it is shown as a failure probability zone. Okay. So what is the failure probability? This zone will give us the failure probability. So traditional approach, we have factor of safety, and now advanced approaches, we have probability of failure probability reason, and then we give the failure. And here, as I mentioned, you can again characterize uncertainty also. Okay. So advanced structural designs are based on probabilistic methods. Okay, where there will be saving on material. Saving on material means it is a process, cumulative process. It will reduce the stresses also, less material, less stresses, and saving on the financial aspects also. So like that. So but then this distribution data should be available for switching over from factor of safety to modern method of advanced reliability engineering. Okay. So here we have this. Now we have been talking about the complex system. Now sometime I have to understand at higher level what is a complex system. Complex systems are the one where we have two major category of system structures and components. So one is called the process system, other one is called safety system. Okay. And here on this slide, I am giving one more important aspect of complex engineering system, that is security risk. So that means earlier we used to talk about safety risk only. Okay. Now there is a security risk. So safety and security have become important given the present context. Because so these three aspects are very important, and safety assurance is assured where security also becomes part of it on a perpetual basis. So what are process systems? Process systems are the one which are required in a plant to generate the throughput, or to provide the output, or to meet the demand. They have to continuously operate and deliver the product or whatever we like. If it is a nuclear plant, it is to generate electricity. So these systems which are used to, like the cooling pumps, normal cooling pumps, then generator, turbine, they are called process systems. There are many systems, we can have a list. Actually, normal cooling, then regulation system, grid power supply system, because grid power, even though nuclear plant or any plant is producing power, but for its operation you require grid power. Sometimes we tap the power which we have produced, but maybe for when the plant is shut down, we don't have grid power, we have to have captive power. But sometimes our dependability is there on the grid power also when the plant is operating. So that kind of thing. So until it is operating on islanding mode. Okay. Then so process system. But if anything is deviating from process system, or anything is going towards unsafe side, then what happens? The safety system, they comes into the play, which were remaining dormant or standby, they get activated and bring the plant to safe state. Safe state may mean shutting down. It may mean complete shutdown. Okay. It may mean also derating, or it may mean activating some system which takes care of, which ensures the fundamental safety aspects. Like shutdown cooling system. Okay. Emergency captive power. When normal power supply fails, then emergency captive power, diesel generator or batteries, they should come into they should provide the power to the plant for emergency purpose, because big machines will be shut down, but the safety system and all, they should get the power. So this is the function of safety systems. Okay. And they have systems like emergency cooling system, shutdown system, emergency captive power system, and things like that. So we have, for getting the idea of complex plant, for our purpose of prognostics and health management or systems approach, implementing systems approach, we require plant to be divided into process system, safety system, and security systems. Okay. And that's how we try to address the reliability and safety issues. Okay. And here the plant safety logic automatically, because from process to safety and safety mode, we come because there is an inbuilt plant logic control logic, protection logic, which activate the safety system, and it brings the plant to safety. Like in a locomotive, there are actuation of braking system using anti-collision devices in railway to bring it to the halt. If they encounter some signal that on the same tracks a train is there from opposite side, then the subject train itself gets stopped due to anti-collision system that has been provided on the deck. So they are called safety systems. Okay, so in reliability engineering, life cycle curve or bathtub curve provides and it connects from theory to the practical side. Okay, and it gives complete life cycle behavior of a component. But before that, the question comes how the bathtub curve was built. Okay, it is built by, suppose you have a electric bulb and you want to find out the life of the bulb. You want to find out the failure mechanism, because while fabrication or manufacturing itself, if you can eliminate some fault, when it goes into the system, the bulb goes into the field as a supply to the user, then they should not encounter problems. Okay, so what will happen is, initially the failures will be more because the component has been fabricated. So it could be quality related issues, it could be learning factors. So the moment it is put, so let's say if you want to understand a typical bulb, 40 watt bulb, and we want to understand its behavior, so we'll put 140 watt bulb under the test, and we'll see how they are performing. Definitely some will fail. Okay, so the advantage is why these bulbs are failing. It is a quality related issue, or it is fabrication related issue, or it is a learning related issue. What is the issue that is there with the bulb? So these are called infant mortality failure. So once we eliminate these failures, then I think we get a very straight curve. Okay, and this is called useful life period or constant failure rate, because the failure rates are constant in this region. Okay, so these are the observed failure rate. So this is called decreasing failure rate, infant mortality period region. This is called constant failure rate region, and this is increasing failure rate region, that is aging. Now for that component, of course, for bulb this phenomena doesn't apply. Bulb is something which will either be healthy or it will fail. It doesn't have in between state. But let's say for a pump, there will be aging period. So failures will increase suddenly, and you will know that after a certain period, let's say 10 to 40 years of life, constant failure life, the pumps are failing in the plant more. And what it says? It says the time has come to upgrade from maintenance to refurbishment of that means do complete overhaul of the pump and replace the component to the extent possible, or replace the pump itself, whichever is economical for the plant, and go for it. So this is a constant value. Now you see, I showed you in previous slide, reliability is dropping. So that means once we do maintenance, the reliability is assumed to be, let us say it has gone to 1, but then it will drop over a period of time. Okay, then what? So if that is the case, it will how the constant observed rate. So it is basically meeting both the theory and practice. We perform maintenance. Okay, so initially the reliability was 1. Let us say this block. Okay, yellow block, and then reliability started coming down. Of course, we don't allow it to go down. We interrupt somewhere in between only, and again we start the component. So the reliability, just for the understanding, I have made it. It goes to 0 and all, but and then you can see that component's failure rate remain constant. So theoretically also component failure rate remain constant, and practically it remains constant because of maintenance activity. So that's how maintenance and reliability they interact. Okay, and of course these curves, they together, wear out curve and then infant mortality curve, these together they will give us the third curve actually. So it is a joint distribution sort of thing for both. So you can see maintenance is applicable in this region. Okay. Now we are talking about the PHM today, but then as I said earlier, testing used to give the information about the component. So there is something called live testing or accelerated live testing. Okay, the component will be tested till it fails. So one is we'll get an idea. I'm using the word it will get an idea, but the important thing was it will be giving what are the failure weak parts or how in stress. So how you get the idea about it. Let's say your use stress for a structure was something we can characterize by U. So we will test the component under 3 stresses. SL1 level 1 stress, SL2 level third stress, and medium stress, use stress. So you see here we have 3 stress level. We have tested the component and the stress level we have varied. This is a use stress here. So SL1, SL2 and SL3. Now we got, let us say, 3 points. Okay. And these 3 points are available us. Now failures are available to us. So we can derive, so this particular factor, it is called acceleration factor. Acceleration factor is nothing but life, use stress divided by accelerated stress. So this is called acceleration. Then it can be in terms of mean time to failure also. So use stress about accelerated stress. So that is give acceleration factor. So in nutshell, live testing involves testing of the component which have been designed, fabricated under higher stress at 3 stress levels, so that we can get curve actually. 3 stresses, and then we will derive the kind of acceleration factor that we used to characterize or to investigate the failure mode or failure types. And here the Weibull distribution has been found to be very, very useful for live test of the experiment. So this is a live test curve, okay, where 3 testings are done. So L1, L2, L3 we have here, and then we can derive the live stress upon accelerated stress. Okay, use stress upon accelerated stress. So this is the advantage. You can see any book or even on internet, you will find the information how it is used actually. So now I was talking about uncertainty. Uncertainty is characterization. It has got something like, you have the population and of test population, and then you have this normal. It is let us say we assume that it is expressed by a normal distribution. Normal distribution is expressed by n stands for normal, and mean value and standard deviation, and that's how you have bell-shaped curve here. And then this is the mean value, and we can have a 90% confidence interval. So 95 will come here and 5% will come here, and complete area under the curve, it will give us, let's say if it is mu plus 3 sigma, so 99.7% area is covered. But let me give you some special information that on the tail end there is not much data available either this side or that side. So sometimes the extrapolation, interpolation and many techniques are used to understand the sigma. So mu minus sigma, mu plus sigma, 2 sigma, 3 sigma and minus 3 sigma and minus 2 sigma, and that's how the bell-shaped curve is built. Okay, so if suppose mean value is 22.30 and then upper bound is 22.300, lower bound is this much. So to be on safer side, I will take this value, and this is what precisely we were losing in our remaining useful life because we were using always a mean value. So we were missing on this 300 hours actually. This is just, you can see upper higher side the lives are not available because of fear of that the component will fail. But how we have solved this problem? We have solved by tracking. Tracking the degradation. So Probabilistic method, prognostics, health management. This slide, in a mathematical term, it explains what are the advantages here. Okay, now we saw definition of reliability, mathematical expression, also the structural reliability we have seen, and then number of cycles discussion we have done, role of reliability in particular. So, structural reliability is a probabilistic reliability wherein we have to have data. All advanced methods are built on structural reliability. Let us say for seismic analysis, probabilistic analysis is used actually. Role of predictive maintenance, a model of the plant considering the safety system, process system, security systems, normal distribution for uncertainty characterization, and bathtub curve. So, we have almost seen the core of the reliability engineering. Probably one or two problems we can see in different books and you will get a fair idea about it. And probably I will request all of you to read distribution that are available, continuous distribution, then constant this continuous is one, like normal distribution is a continuous distribution. Discrete distribution means where the data is not continuous. It is called like number of component field. So, it is a discrete discrete data is available. So, continuous discrete distribution, Poisson distribution, continuous distribution, binomial distribution is distributed. So, you can see probably those readings will help you out to get interface with the subject here, because we are at the end of the day we are talking about systems approach as a probabilistic approach here.